This presentation is going to focus on chemical reactions. Most specifically, we're going to look at double replacement reactions. These are known as precipitation reactions because a solid is formed. And to be able to determine if a solid has formed, you will need to use the solubility rules. And from that, you need to be able to write complete ionic equations and net ionic equations. So before we can do that, let's take a look at writing the molecular equation. We're going to combine potassium iodide with lead 2 nitrate. And so the aqueous is telling us that it is a compound dissolved in water. So it's an aqueous solution of each of these compounds. What does that really mean, though? It means that these are separate ions floating around in the solution. Notice that Ki is really K plus and iodine. That's what the aqueous means. And that lead 2 nitrate really is Pb with a +2 charge and 2 nitrates. Where did those 2 nitrates come from? They came from the fact that in this compound there are always 2 nitrates that were originally attached to lead. But in aqueous solution, they are ions. And so what happens when you mix that as a solid is formed? You'll be able to determine what is that solid formed using solubility rules and what is still remaining in the aqueous layer or as ions. To predict products then, the key is to bring one ion of each over to the product side. Don't focus the fact that you have 2 nitrates here. Only bring one over. The other rule to follow when you're doing double replacements is the cation switch partners. Alright, so it looks something like this. K is now attached to the other anion, and the lead is attached to the other anion. You write your charges for each of these so that you can crisscross those to write a balanced compound, which looks like this. You use your solubility rules. Now when I use solubility rules, I always use the cation rule first, and there's only one cation rule that states anything attached to potassium, sodium, lithium, and ammonium are automatically soluble. Something that is soluble means that it is aqueous. It remains as ions in the solution. In the lead 2 iodide, the rule that I would be using is there is one that states the halogens are soluble except, remember halogens are group 7A, except when they're attached to lead with a +2 charge. So in this example, lead 2 iodide is the solid and potassium nitrate is the still remaining as ions in the solution. And it looks like this in the chemical reaction below. And so looking at a double replacement reaction, we want to be able to really describe what's happening on the ion level, and that's where complete and net ionic equations come into play. Alright, let's take a look at the molecular equation. The molecular is basically predicting the products, and before we can write complete and net ionic equations, you need to balance the reaction, and so that's where the coefficients are coming from. Before we can write complete ionic equations, let's just take a look at how to divide these into ions. Now anything that has an aqueous after it are going to exist in the solution as ions. Let's just see how that works. Alright, so let's take a look at taking lead 2 nitrate and dividing it into ions. It would remain as a lead with a +2 charge. How do I know it's a +2 charge? Because there's 2 nitrates attached to it, and each nitrate is a -1. So a total is a -2 from this side attached to this lead. And the charge of a transition metal remains the same during the chemical reaction. So this would split into lead +2 with 2 nitrates. Alright, so this is part of a preliminary on how to write the complete ionic equations. Let's take a look at this potassium nitrate where we had to write a 2 in it to balance the chemical equation. By putting the 2 in front of here, as in balancing the equation, this 2 affects everything that's in the compound. So I will have 2 potassium ions and 2 nitrates. You'll have to recognize your polyatomics to do complete ionic equations. So starting from the molecular equation, we're going to write a complete ionic, which shows all of the ions that are involved in the reaction. So everything that is aqueous has been divided into ions. And notice, again, when you put a 2 in front of a compound, how it affects everything that's in that compound. And so everything is written as an ion except for the solid. You keep that together. To get the net ionic, which shows only the ions involved in the solid, you're going to cross out anything that appears on opposite point. I have 2 potassiums on each side. Notice I have 2 nitrates, which nicely cross out. And everything that's left over is going to be those ions involved in making the solid. And so writing the equation as it would appear, the net ionic equation would appear as this below. Notice that I have 2 iodines attached to lead. It also corresponds to the exact amount of iodines on the reactant side. Here's another equation. Again, we're going to do a double replacement reaction where the cations switch places. You bring 1 ion of each over to the product side. This represents the product side. And then put each of them with charges. So here they are with charges. And then crisscross them to make a balanced compound. These are your balanced compounds. But again, you need to use your solubility rules to determine if a solid has formed. Again, the cation rule, again, anything attached to sodium, potassium, lithium, or ammonium is automatically aqueous. So this is, on the product side, an aqueous compound. Do not assume that this automatically makes a solid. However, the sulfate rule states that it is soluble unless attached to lead with a +2 charge. And so here is your solid. Let's write complete and net ionic equations from this molecular equation. Again, before I can do that, I need to balance this, and so I need to put a 2 there. Continuing on over here, let's just review again on how these would split apart if they appear as aqueous compounds. How would they split apart to make the ions? It's a preliminary step for you to understand on how to write complete ionic equations. Notice that this lead acetate would divide into a lead with a +2, and because there's 2 acetates on the side, the 2 acetates also appear on this side. Think about how sodium sulfate would go into ions. There's a Na2 here. Would it appear as an Na2 with a +1 charge? No. Make sure you write your coefficients in front. The only subscripts that appear as ions are those that make up the polyatomic. Any subscripts are for the polyatomics. But to tell me how many I have of each, it goes in front, just like in a balanced equation. Look at this one, 2 sodium acetate. So that 2 affects the sodium ion and it affects the acetate ion. Alright, so let's write the complete ionic equation. And I've done this from the molecular equation. I have split it up in here. Our next step is to cross out the ions that appear on opposite sides. Again, checkpoint. If you can't cross them out, then you, again, either balanced it wrong, predict products incorrectly, or didn't make them into ions correctly. Know that you've done it right because the ions left over are going to be found in your solid. And so after writing the complete ionic equation, the ones that were left here are the net ionic. Let's take a look at this one again. Again, you're going to switch your cations. Check your charges. Check your solubility rules. Remember, anything attached to sodium or lithium automatically makes it aqueous. So this is a no reaction. When you have 2 aqueous products, it means then you should write no reaction on the exam because a double replacement needs to have a solid as one of the products. This is an example. This is an example of one of the double replacements found in your lab. You are going to be mixing copper sulfate with a solution of sodium hydroxide from your chem kit. It makes a solid that looks similar to this. Again, you're going to switch the ions. Now, what charge would copper have on this side? Because copper is a transition metal. Use the clue from the compound that it is over here. If you had to name it, you always had to look at what anion was attached to it so that you would know the charge of the transition metal. Sulfate is a -2, so this means copper is a +2. That is continued onto this side. So copper is now attached to the other anion and sodium is attached to the other ion. Cross it down and then you will see when you use your solubility rules that hydroxides are insoluble unless they're attached to sodium, lithium, or potassium, because notice this is aqueous but it's attached to sodium. This is attached to copper, so this makes it insoluble. That's the solid that was formed. When something is insoluble, you represent it by an S, meaning a solid formed. Sodium sulfate, because it's attached to a sodium, makes it aqueous, so he would remain as ions in the solution. So to write the complete ionic, again, you must make sure that you balance the equation. So this is the balanced equation. This is an example of how to split those apart into ions, again keeping the solid together. So this would be an example of the complete ionic equation. And to write the net ionic, again you take the time to cross out ions that appear on opposite sides. So here is all of the ions involved in making your net ionic equation. Again, notice that I have 2 hydroxides attached to copper. I also have 2 hydroxides over here. So however many I have in my product should also be reflected as to how many I have on the reactant side.